All right, we are very soon going to start talking about Laplace transforms and the transform methods for solving differential equations. Before we do that, we're going to review a topic from Calc 2. And it's assumed that you've seen this and assumed that you can do it. So I'm just going to do some examples and as a reminder of what's expected. So our focus is on partial fractions. And this is going to be a tool we're going to make extensive use of soon. And the thing is, starting off with an example, the thing is, when you combine terms, you combine fractions, the idea is you want to find a common denominator, translate everything to have a common denominator, bring things together, and then simplify. The problem is that this thing that we call simplifying isn't always simplifying and makes things harder. So if you have something that's been simplified or condensed, the question then becomes is how do you undo it? So let's look at an example going forward, and then we'll go backwards and try to undo this. If you have a fraction like this, and you're subtracting these two fractions, the first thing is to recognize the common denominator is just the product of the two denominators. So if I take my 2 minus x3 and my 4 over x minus 2, first thing I want to do is make everything look like it has a denominator of x minus 3 times x minus 2. So for the first term, I'm going to multiply top and bottom by x minus 2. And the second one, I'm going to multiply top and bottom by x minus 3. And if I do that, I'm going to get 6 times x minus 2 over x minus 3 times x minus 2 minus the quantity 4 minus x over 3. And the denominator now is the same thing. So when I bring them together, I can take my 6x minus 12 from this term and subtract the 4x minus 12 from that term. And the denominator is going to be the x minus 3 times x minus 2. And if I expand that out, I can write that as x squared minus 5x plus 6. Now I've got a 6x minus 4x is 2x. Minus 12 minus a minus 12 is 0. And I end up with 2x over x squared minus 5x plus 6. And for whatever reason, we call that simplifying, when in fact it's really not. It's making things harder. And the question then becomes is what happens if I have to do an antiderivative of 2x over x squared minus 5x plus 6. Working with this is hard, but working with this is much easier. So the question is how do I go from this back up to there? And the idea is this. I'm assuming I have some p of x divided by q of x. P of x is a polynomial. Q of x is a polynomial. And we're going to assume the degree of p of x is less than the degree of q of x. If it's not, then you can do some artificial integration or not integration, division. And you can divide it out and turn it into something polynomial plus a polynomial in this form. Again, we're assuming at this point you've seen that and you know how to do that. The next step is you take the denominator, q of x, and you factor it as much as you can. And this is the part that can be the most difficult, is we write out the most general expansion. And here's the key things that could been used originally. Because you don't know what it came from, so you have to just imagine it's the worst possible thing and write it out in that form and then see what it means. Once you do that, you just solve for some unknowns. So let's start with this and see how we go through and do that. So suppose we have 2x over x squared minus 5x plus 6. I'm going to factor the denominator. We already know, be careful, that is x minus 2 times x minus 3. And of all the things who have a common denominator of this, it's going to be something over x minus 2 plus something over x minus 3. Now the question then becomes, what is A and what is B? And the way I'm going to address that is I'm going to multiply. So I'm going to start with this expression, and I'm going to multiply both sides by this denominator. So I get 2x is equal to A over x minus 2 plus B over x minus 3 times x minus 2 times x minus 3. And then when I multiply that through, I get this times the first thing, and I get A over x minus 2 times the product x minus 2 times x minus 3. The second term is this B over x minus 3. I have to multiply that by the x minus 2, x minus 3. Notice these things cancel. And I'm left with 2x equals x times x minus 3 plus b times x minus 2. And again, I want to know what a and b is, but the thing is, this has to be true for all x. So in this particular case, I can plug in some clever values for x. So notice if I let x equals 2, I get 2 times 2 is a times 2 minus 3 plus b times 2 minus 2. This becomes 0. So I get 4 equals minus a, so a equals minus 4. Now I would like to make that go away, so I let x equals 3. If I do that, I get 2 times 3 equals a times 3 minus 3 plus b times 3 minus 2. So this becomes, I get 6 equals 0 plus b times 1, so b equals 6. So my original expression is that thing. And I want to write it in this form, but I now know that a is minus 4 and b is 6. And if I don't like working with this, that is much easier to work with. So for example, I can now take the antiderivative of both sides. The integral of this is just going to be minus 4 times log of x minus 2 plus 6 times log of x minus 3 plus a constant. So this is much easier to work with, and I would make the claim this is the simplified version that we should have stayed with. So let's basically just go through and do some examples. So for example, suppose I have 5x over x squared plus 4x minus 32. If I factor the denominator, that's going to be what? X plus 8 times x minus 4, because 4 times 8 is 32. Is that correct? Minus 8, plus 8 minus 4. Okay. And now the most general way to write this is going to be something over x plus 8 plus something over x minus 4. The question is what is a and b? So if I multiply both sides by the quantity x plus 8 times x minus 4, I get 5x. So what is this? This is 8 over x plus 8 plus b over x minus 4 multiplied by the denominator from the original left. So now when I multiply this through, the x plus 8's cancel. I get an x minus 4 And here the x minus 4's cancel, so I get b times x plus 8. So now if I let x equals 4, I can make that go away. So I get 5 times 4 equals a times 4 minus 4 plus b times 4 plus 8. So 20, this is going to be 0, equals 12b. b equals 20 twelfths. Now to make that go away, I let x equals minus 8. And what do I get? I'm going to get on the left 5 times minus 8. It's going to be a times 80, minus 8 minus 4 plus b times minus 8 plus 8. That's 0. So I get minus 40 is minus 12a. So a is minus 40 over minus 12. So my original fraction, 5x over x squared plus 4x minus 32, is going to be a. I'm going to write that as 40 twelfths over x plus 8. Then plus b, which is 20 twelfths over x minus 4. And again, working with this right-hand side can be much easier than dealing with that left-hand side. This can get complicated, though, when you start working with double roots. So what happens with a double root? Let's start off with an example going forward and ask how could we undo this. Suppose I had those two things and you wanted to combine them into one. Well, in this case, I could just multiply those two things together, but that's not really the easiest to use common denominator. The easiest to use common denominator is going to be x plus 2 squared. So here, if I take this left equation, or left expression, multiply top and bottom by x plus 2 squared, notice now my denominator is the same as the other thing. So when I bring these together, so the numerator now for this is 2x plus 4 plus the 4 from that, and the denominator is x squared plus 2, x plus 2 quantity squared. So this becomes 2x plus 8 over the quantity, and if I expand out x plus 2 quantity squared, I get x squared plus 4x plus 4. So the question we ask is, if you started with this, how do you get this up here? Because again, in many situations, this up here can be much easier to work with than that. All right. So the thing to recognize here is if you have something over x plus 2 squared, you have to be able to count for things whose common denominator would happen to be that. And so that means I got to take care of that and that, because this common denominator is just going to be the same as the denominator of that. So let's work this one backwards. If I had 2x plus 8 over x squared plus 4x plus 4, and I factored the denominator, I would get this. I now have to think about of all of the functions whose common denominator is x plus 2 squared, I have to consider the possibility that this might have been in that original expression. It might not. It's possible a would be 0, but I don't know that in advance, so I have to consider that as an option. Now when I multiply both sides by x plus 2 quantity squared, I'm going to get 2x plus 8 is equal to a over x plus 2 plus b over x plus 2 quantity squared. But then I got to multiply by the denominator. So when I multiply all that out, now when I multiply this through a over x plus 2 times x plus 2 squared, one of the x plus 2 is going to survive, but then I'm going to get b over x plus 2 squared times x plus 2 squared, so that just leaves that by itself. Now, I could let x equals minus 2 and solve for b, and then let x equals 0 and solve for a. I'm going to do this a different way, just because it's good to see different ways to do things, but also in some circumstances, this is actually a little easier, even if it's a little hard to recognize what's going on. So if I expand out this thing, I have something times x plus a constant. Over here I have something times x plus a constant. The only way these two things can be the same is if the x terms are the same, so that if I were to subtract them from both sides, those would cancel. And the constant terms have to be the same. So that means 2x has to equal ax. So a is 2. And, 8 has to equal 2a plus b. But since a equals 2, this is 4 plus b, so b equals 4. And that all means then that, let me just use another page here. If I have 2x plus 8 over x squared plus 4x plus 4, we said was a over x plus 2 plus b over x plus 2 squared. Then we said a is 2 and b is 4. And having started with this, I can now write it in this form. And again, in some circumstances, that right-hand side might be easier to work with than other situations. So let's look at an example of that. Suppose I have 3x plus 1 over x squared plus 6x plus 9. Just like before, I'm going to factor the denominator. And in this case, there's a square, right, or a double root. And so I don't know where this came from. There was probably something like that. But this term has a common denominator that's the same. So I have to consider the possibility that that came from there as well. So now multiplying both sides by x plus 3 quantity squared, it now looks like it's in this form. Now when I multiply the x plus 3 squared through, one of them cancels with that x plus 3, and in this term they both cancel. So now using this the other way, you should immediately see that 3x equals ax, so a equals 3. Or I could do this, because of that x plus 3, I could let x equals minus 3. And this expression still has to hold true, so I'd have 3 times minus 3 plus 1 equals a times minus 3 plus 3 plus b. So minus 9 plus 1 is minus 8 equals b, so I get b equals minus 8. So now I get a equals 3 and b equals minus 8. If you don't like where this comes from, you could just say let x equal 0 and then solve, knowing what b is now. You should get the same thing. Regardless, either way, you started with this, and you should be able to write this as 3 over x plus 3 minus 8 over x plus 3 squared.